Sir, over to you.
Good afternoon, good morning, good evening, depending on where you might be in the world today. We are really excited to have Professor Michael Shur from the Polytechnic Institute in New York. Ken and Dr. Goretta really worked hard to make this happen. We were trying really hard to get him into the schedule last year. We couldn't do that, but I'm really thrilled that it is the first distinguished lecture series for the Chief Scientist Office from the Air Force Office of Scientific Research for 2024. And with that, over to you, Dr. Goretta.
Thanks, Pat. So Michael Shur is one of the world's leading theorists devoted to electrical engineering. Taking theory to practical applications is a specialty of his. Toward that end, he has 17 issued patents with many more in the works. He has started 4 or 5 companies already. I presume there are more in the works there as well. Michael began his career at the IAFO Physico-Technical Institute in St. Petersburg. That's one of Russia's absolute best. He was part of the Russian diaspora of the last millennium, worked at a few places in the United States, eventually in 1996 settled at RPI. His research there has, as of last week at least, produced more than 1,600 papers, more than 41,000 citations. He's a fellow of more societies than I can care to list and life fellow of many of them. We're fortunate to have him in our portfolio now. He and a buddy pitched something called ratchet rectification, which is a new mechanism for unidirectional displacement of charge. And it can do so at very low energy. It may have near and far-term applications for terahertz technology. When Michael agreed to do a seminar, he offered us a number of possible topics. This is the one that won the vote. So with that, Michael, could you take it away, please?
Okay, well, thank you so very much for your kind introduction. And the topic of my presentation today is Terahertz communication and sensing technology. And much of this work actually is supported by AFOSR. And I feel that this technology is somewhat similar to avalanche that is about to happen. You are in the mountain and all is quiet. There are lots of snow and snow is still coming, but it's very close to avalanche to happen. And I will explain why. Why I expect dramatic developments in terahertz communication and sensing technology. This is the outline of my talk.
You need to advance your screen.
Yeah, I do. I will talk about the famous terahertz gap. I will discuss mobile devices and 6G communication. Talk about new counterintuitive physics of terahertz electronics that we need to understand and use in order to bridge the terahertz gap. And then I will talk about vector detection and light of sight detection and spectroscopy, which is all important for 6G communication. I will discuss application of silicon, advanced silicon technology for 6G communication. And the good news is that this technology is available in the United States, in my opinion. And then I will talk about terahertz sensing technology and application of terahertz sensing, which I expect will blossom once 6G communication is enabled, because once you have this technology, you could make also terahertz sensing affordable and practical, following by conclusions. So the famous terahertz gap is roughly between 100 GHz and 30 terahertz. And why? Why all of a sudden the gap? Well, the reason is fairly simple. The photon energy at 1 terahertz is much smaller than room temperature thermal energy. And therefore it's very hard to make a laser, because 2 levels to create inverse population would be close enough at 4.2 millielectron volts, so it's difficult really not to have the occupation very different. On the other hand, the cutoff frequency, as you see on this slide, you actually it's hard to approach 1 terahertz. Even though some of these lines kind of close at about 20 nanometer or so. But in fact, this is the upper bound for the cutoff frequency. The actual cutoff frequency tends to be lower. And therefore, electronics is kind of running out of steam, conventional electronics. And even though today we have a 3 nanometer technology, like in iPhone 15 Pro, for example, but in fact the channel length is about 20 nanometers. So this slide is somewhere here. So that's where the gap. And if you look at the history of electromagnetic spectrum, humans started using lighting from fire about 600,000 years ago. Even though humanoids and humans appeared at least 2 million years ago. So it took them a long time to understand that they could use fire. And then about more than 500,000 years took for humans to understand that you could produce candles. And the first lamp that I know of, based on research, when they decided to investigate how to make better light, was 1784 by a student of famous scientist Lavoisier, who was guillotined during the French Revolution. But already in 1792 was the first application, gaslighting, and then X-rays were discovered, first radio transmission, first light-emitting diode, 1907, first laser, 1960. But terahertz technology was only born in 1980s, in the beginning of 1980s. So it's about 40 years old. And now, the new possible application for terahertz technology is emerging, which is 6G communication. And let's talk about it, why it is important, why it is unavoidable. First, let's look at this amazing slide. Well, now there are about 8 billion people in the world, 8 billion people. But there are already about 18 billion, oh, not yet 18, maybe 17 billion mobile devices. And if you look at mobile phones, more than 6 trillion. Oh, it says billions, it should say, sorry, billions, okay. Mobile phones. So it's actually probably one of the most important technologies of today. And if you look out of this about 7 billion smartphones, almost 2 billion are 5G. And what is 5G? Basically, 4G, 5G, and beyond 5G, which is 6G, are determined by the frequency, by the carrying frequency. 4G is about 2.4 or 5.8 GHz. That's your typical Wi-Fi connection of your internet at home. 5G allegedly goes to 28 GHz. Even very few phones actually operate at that frequency. Usually, you are still at about 5 GHz or so. And beyond 5G would be 240 to 320 GHz. And why? Why do we need it? What's the problem? Why not to stay with 5G? Even though, as I say, there's still a lot of place, a lot of potential to improve, to go actually to 28 GHz frequency. Now, that is the reason. Because the global data traffic increases, and increases exponentially. And this is a log scale, so actually this is a lot. And basically in 2028, even full 5G capacity will not be enough to support global mobile data traffic. So it's unavoidable that you need something better, and something better is 6G. So there's a comparison of 6G to 5G and to 4G. And as we see, this is really dramatic improvement. We are talking about orders of magnitude improvement. And once you reach there would be many applications that would open up. Of course, smartphones, online trading, telemedicine, driverless driving, which is tried today, but you know that occasionally cars crash. virtual reality, 8K for public sports streaming, teleconferences, telemedicine, and maybe also 3D video conferencing. And once that happens, also sensors for industrial control, radars, medical and rehabilitation applications, for cybersecurity, for defense applications, would be also enabled. And then some speculation that actually Apple is going to build in Terahertz technology into its smartwatches. So I already made some kind of prediction for the future, and this is a dangerous occupation. There are a couple of pictures illustrating that this is really dangerous and difficult thing to do, but okay, let me risk it. And this is what I'm thinking. The interest curve to terahertz communication technology, to 6G primarily, starting as 2020, increases sharply. And it's not yet reflected by global market for terahertz technology. So it will be struggling, according to projections from financial analysts, it will be struggling to reach $1 billion and exceed $1 billion. So we are at the point where we expect that that will happen. This year would be more than 1 billion. Okay, but I think, and this is a dangerous prediction. Maybe I will be sorry for this graph. I think that this is greatly underestimated because there's new physics, new approaches, new technology are emerging that will make 6G and terahertz communication possible at a greatly reduced cost. But I think I'm not alone in this optimistic prediction. But because, as you see here, all these companies work on terahertz communications, invested quite a bit of money. We are at a situation now where kind of much innovation actually happens in industry. And industry, they're not disclosing everything that they do, but what they disclose looks very interesting and very exciting. And one feature of that communication, 6G communication, that contrary to what you have today with your smartphone, when communication is broadband, it will also have to involve line-of-sight communication. And this slide shows, well, this is a defense application, but anyway, it shows that there is direct communication over the distances about 1 kilometer, and broadband communication at the distances where a team located, maybe limited to 100 meters or so. And the reason for that is attenuation of 300 gigahertz radiation in the atmosphere. Compare to 100 and let's say 250, and you see a great increase in duration. And therefore, this is a challenge to be addressed. Even maybe better illustration of this challenge is comparison what you could do with broadband and directional communication. And data rate here could be an order of magnitude higher, But another applications that could emerge, which is less of a challenge, and from one point of view and from another point of view still a great challenge, is to have communication on a computer chip. Today, the speed of computers, the clock rate, so it has saturated. It hasn't much changed for the last 10 years or so, because it's not limited to a greatly improved technology for an active device. It's limited by interconnects and contacts. And so if you can go to wireless interconnects on a computer chip, that becomes very important, especially because the chips nowadays reach dimensions like 20 centimeters by 20 centimeters. So to communicate with at such distances, Terahertz technology is perfect because you have many photons for the unit of energy, because each photon at Terahertz, at 1 terahertz is only 4 millielectron volts. But to do it, to develop this technology, to go in order of magnitude higher in frequency compared to 5G, we have to understand and appreciate new counterintuitive physics of modern devices. And first, I explain it just in few short sentences what it is, but then I will cover it in a more detailed way. And this is my explanation. If you recall our introductory course in quantum mechanics, or even in physics 1, okay, we are told that electrons have particle and wave-like properties at the same time. Going all the way back to the Borg wavelengths and to determine their position in space and evolution, we could solve wave equation, Schrödinger equation for the wave function. And this is correct and very important. But there is another state of electrons, when electrons are many. And electrons, when there are many electrons, they behave like a fluid, It's like, you know, one individual is one individual. But when you have 1,000 people demonstrating, they behave like a fluid in some way. Okay, so this fluid has lots of similarities to water fluid. And here there's a picture from Hokusai, famous Japanese painter. Really great pictures. And what you could do, you could observe or stimulate all these phenomena that are richly represented in this picture in electronic fluid. So you have to account for that fluid-like behavior when electron concentration is high and dimensions are small. And another new point that I want to make, that you know that there is superconductivity at lower temperatures, but a channel of a semiconductor device, if the channel is short enough, it's a room temperature superconductor. Why? Because electrons, you could understand it in this way. Inside of a semiconductor device, electrons move with the thermal velocity because of thermal energy. And therefore, on average, they spend very little time inside of the device. And during this time, they might not have enough time to collide with impurities or lattice vibrations. It takes certain lengths called mean free path to be able to for electron to collide. And if the channel much shorter than the mean free path, there are no collisions. And we have to account for that. It has absolutely dramatic consequences. So, in a nutshell, water supports water waves, air supports pressure waves, sound waves, but electron fluid supports wave of electron density. And these waves are called plasma waves. And velocities, for water waves from 1 to 200 meters per second, for sound waves from 1 to 50 meters per second. And for plasma waves, which are waves of electron density, from 10 to the 5th to 10 to the 6th. 10 to the 6th is more likely to be, something around 10 to the 6th. So only about 300 times smaller than the speed of light. It's very fast. And therefore, if we use plasmonic waves for trying to build electronic devices, it's easier to reach terahertz electronics, easier to make terahertz devices using plasmonic regimes of operation. And now let's look what happens in a very short device that is much smaller than the mean free path. So this is error mean free path, and this is the dimension of the device. And as I say, with this velocity, it's out of the device or Fermi velocity, which is on the order of 10 to the 5th meter per second or larger. Okay, it spends very little time inside the device and hits the contacts. Now, what happens at the contacts? Well, simplifying it very much, if the contact is metal, in a metal, scattering is very intense. Metals are very conductive because there are lots and lots of electrons, but the scattering is very, very intense. So these electrons immediately met by other hungry electrons that take impurities and all that, and interface states, whatever, and they lose their directed velocity, And that's why there's this additional scattering that you could understand that way. And it is important at distances shorter than the mean-free path. And this is mean-free path in silicon. It's 300 degrees, and it's 77 and 300. And this is the channel length, typical channel length. Let's say global foundry, 20 nanometer SOI process, beautiful process, a dream to have, 20 nanometers. Even 3 nanometer technology for TSMC channel would probably be around 18 nanometers. But it is shorter than the mean-free path. So this physics is very important there. And what happens since this scattering? We conclude that actually, well, there is no conventional mobility because it's ballistic motion, no scattering. But there is measured mobility. And this measured mobility has effective scattering time, which is proportional to the transit time. So we come to a conclusion that the measured mobility should go to 0 when N goes to 0. That's, of course, very strong statement, And we first made this statement in 1991, but only, and worked more on it, but anyway, only in 2004 we were able to confirm it experimentally. In 2016, there was a much better paper from MIT. You see this beautiful, nearly linear trend. So mobility indeed decreases. So we now understand that we should take care of the contacts even more in a short channel device. And we also understand one point that is extremely important. Since this is the dominant mechanism of scattering, right, then conventional scattering mechanisms play smaller role. And that's one of the reasons why the idea to replace silicon with gallium arsenide in VLSI basically failed. Because once you start scaling to 20 nanometers or so, it doesn't really matter that gallium arsenide is much more conductive. Mobility is about 10 times larger in longer samples, like 1 micron, or 2 micron samples, or 1 millimeter samples, whatever, right? You go to 20 nanometers, and this advantage is really diminished. Okay, so we remember that this ballistic transport, ballistic mobility. That's one new physics must be accounted for. But also, here's what is very important. This is all the idea how transistors operate. They operate and they could switch during the time which is equal to the transit time with the drift velocity, not some velocity, drift velocity, because that's how quickly you can supply electrons to the channel or remove them from the channel. So the higher is mobility, the larger is velocity, and the smaller is switching time, or the higher is frequency of operation. Beautiful, beautiful. Make device shorter, you reach higher frequency. Use higher mobility, and you reach higher frequency. But this is not really true if you reduce dimensions too much or increase mobility. Now we're talking about real mobility, not ballistic mobility, too much. Because what happens? These are numerical calculations, analytical calculations, all merged together. But what happens once electrons become too mobile, the waves of electron density are excited, and they continue during the scattering time. So if the scattering time is too long, there would be oscillations of electron density during this time. And it's like you take a glass and hit it, let's say, with a knife gently, but the sound continues for a long time. Okay, so that's the idea. So in fact, with very high mobility, you predict that because of this wave-like behavior, this switching time will increase and the cutoff frequency will decrease until you get to this saturation, which is so-called viscous regime, because electron fluid have also viscosity, just as conventional fluid has. And these are calculations that show that this effect could be very important even in devices as long as 130 nanometers. And this is another calculation for 20 nanometers, 65, 130. So this is extremely important effect. And now, if scattering is too strong, then this plasma wave decay. But they take some distance to decay. They don't decay immediately. And this distance becomes shorter and shorter if you increase the terahertz frequency, because excitation immediately goes as a displacement current through the gate contact of the device. But what happens even in this regime, when you have no plasma waves, is the following. If you shine radiation on this device, and terahertz radiation, the wavelength of this radiation will be much larger than the device dimensions. It would be on the order of hundreds of microns, if not a millimeter, 300 gigahertz at 1 millimeter. And devices micrometer dimensions even taking contacts into account. So you could think that some kind of a plane wave impinges on the device. And when it impinges on the device, the streamlines of electric field are crowded near sharp edges of the contacts, like lightning rod collects streamlines from a huge cloud. Same way happens here, exactly the same way. And therefore you induce voltage between the gate and the source, and the gate and the drain, depending on the boundary condition, both are one. And as a result, there is this cosine-like variation of this voltage in time. But device is non-linear, and therefore you have higher terms, cos squared, and this is positive, right? Always positive. Cosine squared always positive. So you have a DC component. So as a result, you could use a transistor to detect radiation. And interestingly enough, that in terms of practical application, is good or better than what is today in the market. So this is a really important mechanism. So anyway, we come to a conclusion that for detection, transistor is a very good device. And the problem mostly is how to achieve radiation out of it. But before that, I want to show the slide showing the maximum modulation frequencies as a function of mobility. And you see that in principle, optimizing the mobility value, optimizing scattering, and optimizing the size of the channel, you can reach terahertz frequencies of modulation. Huge bandwidth, which is good news. And now let's talk about radiation. One mechanism to use is to, based on the difference in reflection coefficients of plasma waves from two contacts. And as a result, you have this instability, now called Michael-Shur instability. And it has been observed experimentally in several papers. The problem is that practically the power generated is very low. It's about nanowatts. And practical applications for terahertz sources start at about 10 microwatts. However, what could be done? We could combine these devices into arrays. So this is one answer. But if there are many, sometimes impression is better, right? So you could combine it into arrays. And our estimates show that doing that, you could achieve at 1 terahertz about 100 milliwatts power. So this is actually work in progress. There is another interesting mechanism too, which is trying to have effects similar to sound boom. So one of these pictures, that's actually a picture of F-18 crossing the sound barrier. But what I did, I showed several of such events because in a plasmonic device, when electrons cross the plasma velocity barrier, direct velocity crosses the plasma velocity barrier, that could be repeated hundreds if not thousand times. And the power could be very, very large. Now, what is very important, we saw that there is new physics. Now, this new physics must directly go into the design of terahertz electronics, of terahertz devices, integrated circuits. You probably would be surprised to hear that in development 3 nanometer process, and there are only 2 companies in the world selling or having 3 nanometers, Samsung and TSMC. TSMC spent $1.5 billion just for design, simulation and design, not for fabrication, not for characterization, not for parameter extraction, just for design, $1.5 billion. Because it's an expensive proposition. If you do anything wrong, it doesn't work, right? So it's very important to have CAD tools. And what these CAD tools have to account for is electronic inertia, which is intimately connected to the ballistic effects. And this is equivalent circuit of a terahertz ballistic effect, where it's split into the segments. And we found out that to reproduce experimental data, we sometimes need to have as many as 200 or more such segments to reproduce non-uniform distribution of electron density oscillations decaying as they propagate across the device. So, once again, water, sound, plasma waves are all waves, okay? And this is a picture, very nice picture from Krieger Museum in Washington, D.C., showing maybe 5 or 6 different phenomena which are all reproduced in electronic fluid. And sound wave oscillation pattern very similar to what happens in some electronic plasma. And we really tried even to design a device which we called electronic fluid. And the device physics involved in simulation should account for ballistic transport, for electron inertia, for ballistic mobility, for overshoot effects, which are effects related to final time to hit electrons, to get energy to electrons, for plasma waves. And all that should come to terahertz applications, enable terahertz applications. And now I want to talk about vector detection, because I already mentioned in the beginning of the talk, when we go to 6G technology, it's very important to have both directed and broadband detection. And for line of sight detection, one way to do it is to detect not just the amplitude of impinging signal, but also its phase. And here, the slide shows schematically how it could be done. If you have 2 antennas that received impinging terahertz radiation, but with different phase, then you could have the situation where adjusting the density of electron in the channel, you change the frequency of plasmonic oscillations, and therefore come to the situation where you have zero detection at only at a certain frequency. And that could be used to measure frequency, making one device, just a single transistor, to behave like a terahertz spectrometer. And we have several papers where we try to develop this idea. Actually, now we are trying, Professor Mona Heller from our department already fabricated some samples. And the very first sample we tried to characterize, unfortunately, it died because of electrostatic discharge, was very sensitive. But we are trying again. So in a couple of months, we might have some experimental data. But that could be used for line of sight detection. And this is TCAT and simulation on different patterns of detection that allow to determine the direction of impinging beam in 3 dimensions. Another application that could be done is frequency to digital conversion. Basically making these spectrometers with different lengths operating at different bands of frequency. And we hopefully, if the devices that we are now fabricating work, we could try to do it. So how to use it, how to enable it using silicon VLSI for 6G communication. But let's first talk about sizes. So animal cell is from 10 to maybe 60 micrometers. And we are now talking about 3 nanometer feature size being built into iPhone 15 Pro, but 1 nanometer claimed in existence by TSMC in development, 1 nanometer technology. So we come to the point where soon we will be able to make a whole integrated circuit within an animal cell. So this is the slide. IBM promises to, they call it VFET technology, and TSMC says they already have 1 nanometer technology, but not yet in production, not yet in production. And one point that why Terahertz technology hasn't developed that fast yet. Look at this price. For $5, you could buy 2 terabyte memory stick. I bought one. Not that I needed it, but $5. But and it worked amazingly, but not for a long time. But anyway, you see the competition. And this is in size the largest transistor wave I know of. They did it for AI applications, because nowadays, of course, everybody has to work on AI. But anyway, 2.6 trillion transistors on one chip, not billion, trillion. And not all are working, for sure, I could guarantee, okay? And to do that requires extreme UV technology. And you see, the TSMC has 33 lasers to produce it. Samsung has 15, Intel has 5. And the Global Foundry has none, but a couple of Micron has. So you can kind of see who is developing, this. And all this technology basically based on wrapping around the channel. So it's a completely different geometry, because conventional geometry works well till about maybe 32, pushing it maybe 25 nanometer channels. So again, this is silicon technology, which is very powerful, and this compares in gallium arsenide market and just system integration market silicon technology. And as you see, the differences between millions and billions. But these millions make these billions possible, because without gallium arsenide today, the smartphone won't work. And gallium nitride already used in advanced technologies like in South Korea, in Japan, for cell stations, gallium nitride. So these are not as many dollars, but they enable very important applications. And I should mention other field effect transistors, but they're all kind of interesting and important. But this technology is extremely important, And this is technology that for so many applications, even, believe it or not, even possibly for terahertz technology, could compete. So this is technology of the future, metal oxide thin film transistors. So this is another one, but that's not the topic today. Today we talked about communication, and now let's talk about sensing, terahertz sensing. And these are all applications, from wireless communications through Earth remote sensing, all applications. And once from $20,000 for terahertz emitter, we go to $1 made in chip. This all will be possible. This is some examples. This is work pioneered by Professor Zhang. He's one of the brightest American terahertz engineers, Professor X. Zhang. And he used it to find faults in Columbia space tiles. And they couldn't be found by X-ray or ultrasound, but with his machine, they shown his in red. They would do, and he established a company which sold quite a few of such machines to U.S. government. Another application. This is something that you just lived through. COVID-19 pandemic, and this I try to simulate it and to propose what we call pandemic equation. And it's very important to be able to detect viruses, to detect COVID-19 viruses, or new viruses that might emerge. What scares me is that at Davos, they discuss disease X, which I don't know what it is, but they're worried about new epidemics. And Terahertz radiation is perfect for the virus detection, including COVID-19. It is also great for detecting toxic chemicals. The reason is because oscillations of organic molecules are all in terahertz range. They are perfect for this application. Another important applications are in biomedical technology. And it's using it in pharmaceutical. This is commercial. That's used quite a bit. Now they're used for detection of antigens and antibody in blood plasma. There's terahertz DNA spectroscopy. But what's extremely important is using terahertz for cancer detection. And nowadays, if 1 out of 5 Americans will develop skin cancer, so it's really a huge problem. And if not removed in time, could be very dangerous. And the way they do it, they start taking one layer of skin after another layer of skin, testing it and trying to find where the tumor stopped. But there's a way to penetrate with terahertz radiation deep enough and find the difference between cancers and healthy cells. That could be very, very important. This is just a mock-up of future Apple Watch, and I don't know how realistic it is. And this is a picture of a promised terahertz camera chip using 65 nanometer CMOS from a startup in France. And this technology is very powerful for detecting biofluids. In our work, we demonstrated, led by Florida International University Professor Paula, it was demonstrated that the sensitivity orders of magnitude better than for the chemical detection. Another application for detecting morphology and water in plants. That is very needed because the human population is going to increase by 2030 to about 9 billion people. And then it's predicted to saturate at 10 billion. So extra food has to come from somewhere. And there, of course, difficulty because of global warming, whatever the reasons for it. And so it's important now to use water very sparingly because people already started fighting for water. It's more precious resource even than oil. And cancer detection, I already mentioned, not only skin detection, but also there's skin detection basically already at the point becoming commercial. But research is going on liver, lymph detection of cancer in bloodstream, and so on. And this is the picture of this device, interior view systems technology. And one other application that I will brief over very rapidly is terahertz testing under bias. Because since transistors, good transistors, rectify radiation and bad transistors don't, there's tremendous difference. And what you could do, you could scan an IC and see what's coming out at the pins. And then using artificial intelligence, you could interpret the maps generated by terahertz radiation and identify defective integrated circuits. So in conclusion, terahertz gap must be breached to enable 6G communication, and it's inevitable. It has to be done. And bridging terahertz gap requires understanding of new counterintuitive physics of ballistic and plasmonic transistors. And silicon ultra-short channel VLSI can support 300 GHz band for detection and processing, not necessarily for generation. Generation, like in Apple, done with gallium arsenide, will be done with gallium nitride transistors or maybe even diamond transistors. And applications of terahertz sensing, ranging from radioastronomy to chemical detection, medical imaging, will all benefit from 6G development. And thank you so very much for your kind attention.
Thank you, sir. Right now, we are going to transition to our Q&A portion. Again, a reminder for those that would like to ask a question, this is a great opportunity for you to put it into the Q&A feature. And
Hey,
Dr. Greta, I'll
yeah,
turn
Cindy,
it over to you.
while we're waiting for that, maybe I can ask a question. Michael, you say that silicon can support the 300 GB 6G, but not for transmission of terahertz. And you mentioned diamond, gallium nitride, et cetera. Could you say more about what the status of that is? I don't see a whole lot of diamond transistors out there. I don't expect to see one anytime soon, for example.
Okay, the question is that I mentioned that silicon might not support terahertz emission. Actually, I should qualify this system. It's possible that in the end, new types of integrated circuits and new types of ideas could come up that would allow silicon to do it. But now, the most promising material for generation is P-type diamond. P-type diamond is a material that is unique because it has ballistic properties even at 300 GHz and longer channel devices. And longer channel devices could support more power. So this is possible. Maybe it would be even possible to do it in silicon using plasmonic beam devices, but this is still research in progress. So P-diamond, after that, runner-up would be gallium nitride. So these two material systems have big advantages compared to silicon in terms of the parameters, material properties, as potential materials for building terahertz electronics oscillators.
Okay, well, that's good to hear. Military is investing pretty heavily in both of those. Are there any other questions, please?
Dr. Roach has a question.
Yeah, I did. Thanks, Cindy, so very much. Professor Shur, thank you so much for a very informative lecture. I really appreciate it. I did want to ask you, and I apologize, I'm not a theoretical solid-state physicist, but I did grow up as an experimental solid-state physicist. And so my question is more about what it would be the right types of growth potential to create the kinds of solid-state devices you're actually getting at. Would MBE be the right, molecular beam epitaxy be the right way to do this? Would that be the most efficient way? Would it be MOCVD? Molecular beam epitaxy? What method to get at the types of systems that you're asking for would you utilize to grow such exquisite structures? Over.
Okay. I think the question is what kind of technologies we need to develop terahertz electronic devices. In particular, the question was on growth. And growth is epitaxy. The growth would be epitaxy. And this epitaxy could be done by different techniques. If we talk about terahertz emitters where gallium nitride layers are used. One technique, very interesting and very important technique, in my opinion, is what is called MemoCVD, which is migration enhanced heterogeneous chemical vapor deposition technology. It comes closer to MBE, but it could produce even better quality material. And the idea that is to use atomic layer deposition, but with passes of gases overlapping and optimized. And this technique was shown to reduce the dislocation density by 2 orders of magnitude. So that's one technique. Now the problem, of course, is that epitaxy is very expensive. And when you go to new technologies such as gallium nitride, to have full advantage of their properties, you have to grow them on substances such as silicon carbide or diamond or aluminum nitride. And you have to scale up. And now the challenge is to scale to 6 inches. And compare that to silicon technology, which is reached 14-inch crystalline silicon. And if you talk about TFTs, maybe easily 2 meters by 2 meters in continuous line process with 50 nanometer resolution. So you see this technology is difficult, commercially difficult to compete.
No, I appreciate that very much. Thank you so much.
Okay, hey, Michael, we have some questions in Q&A. A couple from John Setnar in our Census Directorate. Number 1, can plasma wave transistor devices amplify?
How do devices is the question how do devices amplify?
Yes.
Well, when you shine terahertz radiation on the device, received either by having contact coupling or using antennas, you excite oscillations of electron density. If there's instability of this electron density, because energy is pumped from the DC current in the system, and I mentioned 2 mechanisms of such instability in my talk. Then there are 2 different regimes of operation. In one regime, this instability develops over distances shorter than the device dimension, and this is oscillator. That doesn't care about the internal impinging radiation. It's the source of radiation itself. In the other regime, however, it's instability where it develops at distances comparable to the channel length. So it's kind of this amplification regime. And as a result, you could have one receiving antenna and one emitting antenna, and the power in the emitting antenna would be larger than the power of the receiving antenna. So that's the mechanism.
Okay, John has a couple more questions, but maybe we'll try someone else first. Leland Norden asks, what limits other ultra-wide bandgap platforms for terahertz? For example, gallium oxide, aluminum nitride, cubic boron nitride. What limits them for platforms for terahertz?
Do I understand your question? You're asking what is the limiting factor, right, in this technology? What is important? What problems are important to solve, right?
Yeah, and then what role might those materials have?
And what is the role of the material? Well, actually, these problems are very numerous, and different founders, different manufacturers, different problems might play a role. So I'll mention a few. One key problem is a problem for contact. You have to have a situation where more voltage drops across the active channel or at least fed into the active channel that drops within the contact without actually coming to the active part of the device. So that's problem number one, contacts. Problem number two, when you scale this device down, you have to have excellent dielectrics separating gate from a channel. So it's very important what happens in the interface. Even in silicon, the bulk mobility is about 1450 centimeters squared per watt per second. You would be a very lucky person. You could celebrate if in a channel of 20 nanometer FET, you measure mobility of 600. Okay? Because of surface scattering. Because of surface scattering. Right? So that's another important problem. Now, another problem is because you don't fabricate one device. You fabricate, as I mentioned, up to 2.7 trillion. So the question comes up, how many work, what's yield, and how many are reliable? Because reliability and yield, they're like brother and sister. So they're very intimately linked.
Yeah, Michael, maybe an easier way to have rephrased that question would be, can you name advantages that a material like aluminum nitride or cubic boron nitride or gallium oxide may have with respect to terahertz technology?
Well, yes, if the question is what kind of advantages we can get using instead of silicon materials like aluminum nitride or gallium nitride, right? Yeah. Is that the question? Yeah. Okay. Well, in order to make a good terahertz emitter, you need to have very little scattering. And these materials have much longer scattering times than silicon. So that's one advantage. Another advantage is higher thermal conductivity because you want to pump a lot of power. The efficiency of converting DC radiation into terahertz radiation, unfortunately, is relatively low. So you have to get this heat out. The thermal conductivity is better. Still, another advantage of these materials that you use in a hand structure higher dielectric materials, larger capacitor for the same separation of gate from the channel. So these are all advantages. And disadvantages, the cost of technology and the difficulty scaling it up.
Yeah.
In other words, for small number of devices, for small substrate, you could greatly outperform silicon, greatly outperform. Once you scale it up, challenges increase exponentially.
Yep. Okay, there's another question from John. I didn't see any gate structures in your device drawings. How are they pinched off?
Okay, you have, unfortunately, as I mentioned, we have problems with your audio. Could you come closer to the mic? We have something about gate structure, right?
Hey, Cindy, why don't you try it? Michael's having trouble hearing me.
Absolutely. Okay.
Third question down.
Third question. Got it. What about transconductance and breakdown voltage?
Okay. The question is about breakdown voltage. It's a very important and relevant question. We have to separate two breakdown voltages at least. One breakdown voltage when you apply voltage between source and drain. And that breakdown voltage, the power that you can get out, roughly proportional to the square of this breakdown voltage. And the breakdown voltage itself, very roughly, proportional to the square of the band gap. So as you see, almost the band gap like a power of 4 advantage. That's why it's very important then to have very wide band gap materials to have a lot of power, okay, for anything. However, there's another breakdown. There's breakdown between gate and the channel, because the distance there is extremely small. However, there's a big advantage too, because you see, to cause a breakdown, you have to have electron energy to exceed band gap, sometimes quite substantially, because you have to satisfy not only energy conservation, not only electron has to give the crystal enough energy to get a hole, to get another electron from the valence band to create a hole, but also momentum conversation has to be maintained. And therefore, you could probably spend as much as 2 energy gaps of energy, right? But if I only apply to the gate voltage below that number, let's say I have a silicon MOSFET, and you know the power that it works at now could be 1.5 volt, or even 1 volt. And the energy gap of silicon is 1.1 volt, and the energy gap of silicon nitride is 9 electron volt. So you would think there's, and therefore the breakdown of silicon, for example, when you make it thin, increases from 0.3 megawatts per centimeter to about 40 megawatts per centimeter, because you can apply 1 volt to a 1 nanometer silicon and don't cause much of a breakdown, but you do cause some. Okay, so it's still an issue, but not as much an issue as the drain to source breakdown.
Wonderful. Thank you, sir. Well, we have reached our 3 o'clock end time, and I just want to say thank you on behalf of AFRL, AFOSR for presenting today. We had a wonderful amount of interaction, so thank you, sir. And at this time, I will close the session for all. Dr. Roach, any closing words?
I want to thank Professor Michael Shur very much for doing this. What a great talk. I want to thank Dr. Ken Goretta for pushing us hard on this. This is really worth it. I think the technology coming from what you're doing, Professor, is phenomenal. Look forward to seeing more from you and certainly more from Dr. Goretta. Back over to you, ma'am.
Thank you all. And again, this presentation will be on YouTube once we receive clearance. And if anybody is interested in getting a copy of the presentation, please email me at cindy.barner@us.af.mil. And to that, have a great day.
Hey, thank you, Michael.